what I'm going to talk about today will be based on this paper, although I'll say a small fraction of what is there in this. Okay, and you will also find lots of other references in these papers, in this paper, okay, the earlier work, including Ornov's papers on double soft theorem. Okay, so let me first say what CHY stands for. CHY is Casazo E1, okay, and so the goal today is that we'll use a formula that CHY wrote down for tree-level scattering amplitudes, okay, in a wide class of theories, okay, that includes Einstein-Maxwell, okay, and our analysis will be based on their formula for the Einstein-Maxwell theory, okay. So that's a formula for tree-level gravity scattering amplitude, tree-level scattering amplitude in standard Einstein gravity, okay, and we will use that to check the soft theorem that we derived last time, okay. That was of course for any generic theory, okay, so it better be true also for the standard Einstein gravity.
Not necessarily tree.
Yeah, so that formula was valid for at the loop level as well, but then it means it should also be valid for tree amplitudes, right? And CHY formula is only for tree amplitudes in standard Einstein gravity, okay, no higher derivative corrections, etc., and that's the theory we'll be working with. So CHY formula gives tree-level scattering S matrix for a wide class of theories which includes Einstein-Maxwell. And our goal will be to use CHY formula to test subleading multiple soft theorem. Well, okay.
Or mutual consistency.
Okay. Let me put it this way.
Yeah.
Yeah, so it's a test of CHY formula, okay. What we have done, of course, is general derivation, so they better be true, right? I mean, unless CHY, there is some underlying assumption that is breaking down in the CHY formula.
But why did you choose Einstein gravity since your formula is very general?
CHY includes gravity, it includes Einstein-Maxwell, so you could have taken some of the external states to a Maxwell, right? But it just requires more, I mean, we have to do a little bit more work, right? So we just looked at the part of the formula that involves only gravity scattering amplitude.
So they don't include any form of their CHY formula don't include Young-Mills.
Yeah, Einstein-Maxwell, okay, Einstein-Maxwell, Maxwell also can include Young-Mills, but they give the ordered amplitude, okay, which is where basically for a given ordering, right, the Young-Mills and Maxwell are more or less the same.
Will you review the CHY a little bit?
Yeah, I'm going to do that, but only for graviton scattering. Okay, I'll give the CHY formula for graviton scattering because that's what we'll be using. Remember, that's probably the only thing I'll do in this lecture, to review CHY scattering formula and then just give the result.
They don't make any softness assumption.
No, they don't make any softness assumption. So the formula that they gave is completely general. Okay, but before I give the CHY scattering formula, okay, I have to give some mathematical background, okay, and that's the background on holomorphic delta functions. Okay, so this is something that we had some confusion with, so let me describe some subtleties. Okay, holomorphic delta function. Okay, so what does it mean? Okay, so here sigma is an abstract complex variable, okay, and f of sigma, okay, small f and capital F, okay, these are two holomorphic functions. Okay, small f and capital F are two holomorphic functions. Okay, so the definition of this that we'll be using is sum over alpha f prime of sigma alpha inverse f of sigma alpha, okay, where sigma alpha are the zeros of f of sigma. Okay, that is f of sigma alpha equal to 0.
It's not magnitude?
No, it's not magnitude. Okay, because then you will lose holomorphic, right? So it's not magnitude. Okay, that's important. So this is the definition of a holomorphic delta function. Okay, so it's similar to the definition of a normal delta function, except that for a normal delta function with real integral, okay, there will be a mode of f prime of sigma alpha inverse. Okay, that's the main difference. Yes.
So suppose I mean the problem then is that if I take f to minus f of sigma inside the delta function,
It will have a minus sign. If so, delta of minus f of sigma, right, will have an extra minus sign.
so the holomorphic delta function is not an even function.
No, it's not an even function.
Is that the subtlety?
That will be one of the subtleties, right? And we'll see what kind of subtlety we encounter. It's not an even function.
You said it's an abstract complex code. It's just z on a plane, right?
Yes, but you are not specifying at this stage what the integration is over. It's integral d sigma, right? Integral d sigma delta of f of sigma is defined by this. Okay, I'll make it more specific as an integral. Okay, so an alternative definition of this, okay, is that this same object can be written as sum over alpha integral over sigma alpha where this is anti-clockwise contour around sigma alpha, okay, with the 1 over 2 pi I factored. Okay, you integrate around each of the zeros of f of sigma. Okay, when you do that by residue theorem, okay, you basically pick up 1 over f prime of sigma alpha times f of sigma alpha, right? That's what this is. Okay, so this expression here is identical to this expression over here.
So do you want to assume that this capital F of sigma doesn't have a pole at sigma equal to sigma alpha?
No, it can have a pole, okay, in which case it may be ill-defined. Right? It's like integral delta x f of x, right, will be ill-defined if f of x blows up at x equal to 0. Right? So something similar will happen here. But this will be the definition, okay, that it will be integral around the zeros of f of sigma, okay, multiplied by whatever function you have. Is this clear?
So it's really what's happening is that you have in mind that this is coming from a two-dimensional delta function mod square and you're taking square root. Holomorphic square.
Well, I don't know whether, yeah, when you,
Roughly.
yeah, roughly it's like that, okay, but this definitely, once I do this, it's concrete, okay, at least for a single variable. We will see that for multiple variable there are some subtleties. Okay? But for single variable, this is the definition of what this means.
So if you want to put them to equal, you will not have to worry about this residue of small f at sigma equal to sigma alpha.
This one?
Yeah.
See, sigma, this vanishes at sigma equal to sigma alpha, right? So this becomes 1 over f prime of sigma alpha times sigma minus sigma alpha.
Oh,
Okay? So then when you use the residue theorem, that you get exactly 1 over f prime of sigma alpha times f of sigma alpha.
It is still due to the second, from the second equation that you have written, sigma is still the normal complex variable. It is the definition
Yes,
for delta.
here is the normal complex variable, it's a complex contour integral, right? This is just an abstract notion. Here it's not clear what you are integrating over.
Abstract is, delta is abstract.
Delta is abstract, right? So because delta is abstract, right, this integral is abstract, right?
right, you can say that this is what you mean and you want to write.
Yeah, this is what you mean, but you will write this. Okay, that's the bottom line, that this is really what we mean by this integral over here. Okay, that it will be integral, contour integrals over the zeros of f of sigma. Now let's see what problem one encounters when you do multiple integrals. So let's suppose that we have an integral of this form, integral dx dy delta of x minus y delta of x plus y f of xy. Okay, x and y are those abstract complex variables, and this is the one that you want to integrate. Okay, and let's try to proceed as you will do in a normal delta function. Okay, for a normal delta function integral. And so let's suppose that we want to do the y integral first. Okay, so normally when you do the y integral for a delta function like this, okay, the first y integral we can either use this delta function or that delta function, okay, to substitute y equal to minus x or y equal to x, okay, and then we can do the x integral, okay, we get the same result. Okay, so let's suppose that we do the y integral with first delta function. Then what we will get is integral dx. The first delta function has argument x minus y, so f prime is minus 1, right? ddy of this is minus 1. Okay, so you get a minus 1. Okay, and then we just set y equal to x everywhere. So delta of x plus x f of xx so this delta of x plus x delta of x 2x, okay, so this gives you minus 1 times half times f 0 0. Okay, you do the x integral with this delta of 2x. Yes, here there is an absolute value, so minus 1. But the same integral now let's do by y integral with second delta function. So then what we will get is integral dx. Okay. Now you have the integral dy delta x plus y, so y will be replaced by minus x, but there is no overall minus sign. So here you get delta of x minus of minus x f of x minus x. Okay, because you are just setting y equal to minus x everywhere. So this is again delta of 2x, so we get half f 0 0. Okay, so you can see that these two are not the same. Okay, there is an extra minus sign. Okay, for a normal delta function, this would have been the same because this would not be minus 1, right? There will be mod, so it will be plus 1 here. Okay, so then both of them will give you plus half times f of 0, 0. Okay, but for these holomorphic delta functions that we have defined here, okay, this gives you minus half, this gives you plus half. Okay, so we have to do some extra work to define integrals of this form. Okay, it's not just enough to say that we treat it as a delta function as we have given here.
Are there not really happening around the contours?
Pardon?
Are there not really something around the contours?
Yeah, there are non-trivial things happening around the contour, but we will give a prescription to fix it here. Okay, so the prescription that we can follow is the following. Okay, that if you are given an integral of this kind, okay, a series of variables and a series of delta functions, okay, we will use the convention that the last integral will be done with the last delta function. Okay, the last but one integral will be done with the last but one delta function, and so on. Okay. Now, of course, you can ask what if we want to do the other way. Okay, suppose you want to do the last integral with respect to the last but one delta function. Okay, you can do that, but you can do that at the cost of exchanging the two delta functions. Okay, and the rule that we can adopt, okay, which gives the consistent answer, is that the delta functions you have to think of as Grassmann objects. Okay, so if you want to change the positions of the two delta functions, you can do that, but that costs a minus sign. Okay, so then with that convention, you say this is the right answer. Okay, because you have used the dy integration with the last delta function. Okay, so sorry, this is not the right answer. The second one is the right answer because you have used the dy with the last delta function, right? Because you have set y equal to minus x. Okay, so this is the right answer. Okay, here, okay, you have used the y integral, but you have used the first delta function. Okay, so this is not the right answer. But what you could have done is that you have to first exchange the positions of the two delta functions. You could have brought this here. Okay, but because the delta functions are like Grassmann objects, when you have brought this here, you pick up a minus sign, okay, and then you apply the same thing. So that minus sign will cancel this minus one and again give you plus half over here.
You can see it is consistent, but what is the meaning of this? Just say delta functions are...
Yeah, the meaning of this is if you take delta function of, say, suppose you have a delta of x1, delta of x2 up to delta of xn. Okay, you make a linear combination. You take a change, make a change of variables. Take x to aij xj. Okay. Normally, this delta function of product over I aij xj, okay, is 1 over mod determinant a times the product over delta of xi, right? Here what you want is 1 over determinant a, not 1 over mod determinant a, right? So the exchange, right, is like a matrix 0, 1, 1, 0, right? So determinant of this is minus 1, right? That's why you have to pick a minus sign when you do the exchange. Okay, and the reason is that in a holomorphic integral, so you will think of this as wedge products, right? So when you make a linear combination there, you pick determinant of a, right, not a mod. Okay, and that has to cancel against the 1 over determinant a, right, that comes from the delta functions.
It's not shown as a volume form, but as a wedge product.
Exactly. You have to think of it as a wedge product. So similar delta function also you have to think of as a Grassmann objects, right? So that interchanging positions for delta functions is a minus sign.
Generalize for f and g arguments of delta function.
Pardon?
X minus 1 and x plus 1 can be replaced by functions of x.
Yes, you can do functions of x and y. So the point is normally you take a determinant. Suppose you replace xi's. Suppose you compare product of delta xi with product of delta of fi of x. Okay, a set of functions x1, x2 to xn to f1, f2. So this object, okay, will be 1 over determinant of del j fi times product over I delta of xi. Okay. For a normal delta function, it would have been mod of determinant of this, right? Here it's just determinant of del j fi. Right? That's why exchange costs a minus sign, because it's like if f2 is x1 and if f1 is x2, right? Then the corresponding determinant will have a 0, 1, 1, 0, right? That determinant is minus 1. So that's what we are seeing here basically.
But does it mean something geometrically? In terms of
Well, I don't know. Okay, I don't know what its meaning geometrically is. Right? This is the way. This is the prescription.
See this expression, the last expression in terms of contour integral.
Yes.
It is normal. There is no extra.
Exactly.
abstraction, right?
That's right.
You are trying to write that as a two-dimensional integral and
No.
localizing it, right?
No. This is one integral.
Right.
Right.
But you are localizing a two-dimensional function. Because
No. This is f of sigma holomorphic function.
Right. So it's a complex coordinate.
Yeah, but that's an abstract complex coordinate, right? All the integrals are one-dimensional here.
Right, precisely. But usually in two-dimensional integration, you have z and z bar coming together.
Yes.
And that's why you don't have a problem.
Exactly.
You are imposing this one-dimensionality, and that's why you are.
Yeah. So this is the definition, right? And with this definition, if you want to be consistent, right, you have to adopt the convention that when you change order of the delta functions, you have to pick up a minus sign. Okay. More generally, this is the rule that when you take delta of fi of x, product over I, right, and write it as a product of a delta of xi or delta, well, suppose fi of x has 0 at x equal to 0, right? Otherwise, of course, it will be xi minus xi alpha, right, where alphas are the xi alpha are the zeros. Okay. But this change of variable will involve this determinant without any mod.
So, this is what we really mean, the contour integral.
Yes, this is what we really mean.
That can be defined even if there are multiple complex variables.
Well, if there are multiple complex variables, you have to say which variable is integrated about which contour, right? Yeah.
Ultimately, we will be integrating over like various different points.
Exactly. So the point is the last one will be integrated about the zeros, about the poles of the last delta function.
If you do it in the contour integral fashion, perhaps you don't have to specify the order, right?
Well, you have to specify this ordering. The fact that the last one will be done with respect to the last.
Delta function. But if you write it as a contour integral,
See, even if when you write it as if you write it as a contour integral, right, then the last one, okay, see, there are several functions, right, which are made to vanish when you write it as a delta function. Okay. Which one you use here, right?
oh, yeah.
That you have to specify. Exactly.
Then if you have like a sigma 1, sigma 2 up to sigma n,
And f1, f2 up to fn.
You change that to x1, x2, x3 if you wish.
Yes.
And then like the change will involve a Jacobian.
Exactly.
And that seems to be precisely.
That's right. So that Jacobian doesn't involve in mod.
So this particular prescription also corresponds to the prescription that the contour integral be first done with the imposition of the last delta.
Yeah. So last contour integral will be done by imposing the last delta function, right? Then the last but one contour integral will be done with the last but one delta function, and so on. Okay. So when you write multiple contour integrals with multiple delta functions, this is what will mean. Okay. And the reason that I am introducing this is because CHY formula will be written in this language. Is this okay? Okay, so then I can now write down the CHY formula. Okay, once we accept that this is the way the delta function has to be interpreted.
In the original CHY formula, this Grassmannian nature or this weight curve.
Well, it was not explicit, right? I think it was implicit in the way.
But they were handling it that way.
Well, they didn't. I mean, the point is, not many calculations were done in the original CHY formula, right? But I think it was implicit that this is the way you have to handle it.
There is definite ordering for the delta function.
Yes, there will be a definite ordering for the delta functions. The point is that unless you are worried about signs, right, you don't worry too much about this ordering, right? And at least in the initial analysis, various kinds of analysis with the CHY formula that people did, they are not really worried very much about the signs, right? So they always did up to signs. Okay, that's why they didn't have to worry too much about this ordering prescription.
Is it always an overall sign? Even if the multiple?
Yeah, meaning if you do it in a different order, right? If you exchange,
It's always
always an overall sign. Okay, so now in graviton amplitude. In CHY prescription. Okay. And I should just say that this is valid in general dimensions. And here is the formula. Okay, it's a complicated formula, but I'll explain. This is a function of sigma a's, P's, and epsilon a's. Okay, so let me try to explain. So I'll keep this here because this will be using this. So sigma 1 to sigma n are complex variables. Okay. They are integrated over in the same sense that I described. Okay. They are integrated with the help of these delta functions. PQR are three numbers between 1 and n. I, j, k are three numbers between 1 and n. Yes, so ijk could be PQR, equal to PQR or not equal to PQR. Okay, it turns out that the final result doesn't depend on this. Okay. Sigma AB is basically sigma A minus sigma B. Okay. IN will be defined later. IN to be defined. So the claim is that you do this integral, okay, from c equal to 1 to n, removing 3 of the elements, okay, any 3 that you like, okay, and this removing 3 elements has to do with the SL to C invariance of the integrand. Okay, it turns out that because of the SL to C invariance, it doesn't matter. You can always keep 3 points fixed. It's the analog of the statement on a Riemann sphere. You can keep 3 points fixed. Okay, on a complex plane, you can keep 3 points fixed. So 3 of the sigmas, okay, you just remove. You don't integrate over them. You can fix them to be anything that you like. Okay, so that's the sigma c integral. Okay, corresponding to that you add this thing over here. Okay. Then here there is a product of delta functions. Okay. Again in this product of delta functions you remove 3 arbitrary a, okay, equal to ijk, okay, and compensate for it by multiplying by this measure factor over here. Okay. What one can show is that if we solve this equation, so this delta function means that we are basically localizing on the zeros of this argument, right? So there are n minus 3 equations, right, because there are n minus 3 delta functions. Okay, so you are localizing on the zeros of those. What you can show is that once you localize on the zeros of those n minus 3 of these delta functions, okay, the corresponding quantities for a equal to ij and k are automatically 0. Okay. See, if you didn't drop a equal to ijk, they will be over considering, right, because the same delta function will appear more than once. Okay. So this, so again let me say, so this means that if you solve, for example, for the sigma is that this is equal to 0 for all a, okay, except a equal to ijk. Okay. Then for a equal to ijk the equations automatically hold. Okay, the corresponding quantities are automatically 0. Okay, so that's one way to justify why you drop this. Okay, but after you drop this, okay,
PIs are independent.
which are independent? Yes, PAs are independent objects. Okay, they are external momenta. For generic P's, okay, you have to also of course satisfy momentum conservation, sum over PA equal to 0. Okay, that's a constant.
So why I don't see the reason why that other 3 will be automatically.
Well, the point it's not easy to see,
okay,
right? But one can show that.
No, but what is the reason? What
basically, it's an SL2C invariance.
I see.
Okay, using SL2. So basically, these n equations are related to each other by SL2C transformation.
For
okay,
arbitrary PAs.
For arbitrary PAs. Okay, as long as you satisfy momentum conservation. So once you satisfy n minus 3 of the equations, the others are automatically satisfied. The other 3 are automatically satisfied.
Just to get some idea, so if I take n equal to 4,
Yes.
say fix a PQ out to be 1, 2, 3.
Yes.
So this looks like just one.
One integral, one delta function. Exactly.
So there, like, what is happening? I mean, I'm doing some integration over something.
Yeah, but the integration, actually integration is fake because you can see there are n minus 3 integrals and n minus 3 equations, right?
Yeah.
So basically the integration basically means that you will get some certain set of solutions. Okay. So if take the n equal to 4 case, right, 3 of these are fixed, right, one sigma integral, okay, and one delta function. Okay. When you solve this, you will find there is a unique equation.
I'm thinking from the point of view of scattering amplitude. So what is that supposed to imply?
So okay. So the point is that you get a unique solution for the sigma 4. Suppose you have fixed sigma 1, sigma 2, sigma 3, right? By solving this, you get a unique solution for sigma 4. Okay. Then you evaluate in, okay, which I am yet to write down, at that value of sigma 4. Okay. And the claim is that that is the scattering amplitude for 4 gravitons. Okay. That's the CHY formula. Okay, similarly, if you do 5 point, right, there are 2 integrals left over, but 2 delta functions. Okay. Again, you can solve it, and you can show in this case there will be 2 independent solutions. Okay. So you sum over those 2 so you evaluate in for those 2 independent solutions, add them up, okay, and the sum of the 2 gives you the 5 graviton amplitude.
So the difficulty is what, like solving this argument of the delta function?
Yes. So if you want to do this directly from this formula, the difficulty is in solving this delta function, right? Because this becomes a polynomial equation, right? For 4 and 5 it's okay, but if you do it for 10, for example, right, it's a polynomial equation of a very high degree, and that in general you cannot solve it analytically.
So there is basically no integration. So does it correspond to the fact that there are topologically inequivalent diagrams?
They are topologically.
Like when you take a in-point scattering amplitude.
Yeah, the point is it is difficult to relate individual solutions here, okay, to individual Feynman diagrams. So it's not that a given contribution here is mixed up between Feynman diagrams. Okay, so it's not that each Feynman diagram corresponds to one particular term from here.
But when you add all the Feynman diagrams, you get this contribution.
That's right.
So you cannot separate out the Feynman diagram contribution.
From this, yes, exactly.
From this.
Yeah.
Is there a vertex operator way of writing this answer?
Well, there is this ambitwisted string, right, where they try to get this from a worldsheet formulation. Okay. But at least the original CHI prescription is general, yeah, and
But
that.
set of sigmas, sigma PQ, etc.
Yes.
Those are like C ghosts of the unintegrated vertex.
Something like that, exactly. Yeah.
But I don't see this sigma ij.
Well, that comes from this. The delta, normally you don't have delta functions, right?
Right.
But this product of delta function, right? The measure is invariant under SL2C only if you add these objects.
So this is for what theory? Oh, this I will tell you.
This I will tell you. I is different for different theories, right?
But the same structure for everything.
For okay, it's not the CHI scattering formula holds for all theories, but it works for a wide class of theories, and the corresponding INs are people have constructed.
There's a dimension.
Pardon?
There's a dimension.
Dimension doesn't enter anywhere here except that PS, when you write PA.PB, right? It's inappropriate dimension, and also when I write down the IN, it will have some inner products. Those will be inappropriate dimensions.
I thought SL2C has something to do with Lorentz group in 3.
No, that SL, yeah, this is independent of that. Okay, this is more like worldsheet SL2C, right? At least when the get it from ambitwister, right? This SL2C is inherited from the worldsheet. Okay, it's some kind of chiral worldsheet theory, right? That's why this is SL2C and not SL2C times SL2C.
So if you had added all those ijk, 3 A's,
Yes.
so in the sum, that would be the total sum will be
A product.
SL2C invariant.
If you put this product, well, yeah, except that it will be ill-defined because it will be like delta f x times delta of x, right? Because these delta functions already set something to 0, right? If you now multiply by another delta function, right? See, it's delta of x1 times delta of x2 plus delta of ax1 plus bx2, right?
I got it.
That's the ill-defined object.
But then, what the origin of the measure, you said that. So something is not invariant.
Yeah, you're dropping some things, right? But what you're dropping, right? Which particular linear combinations you are dropping, right? Is different for different choices of IJK. So corresponding measure is that one.
So n graviton amplitude has been calculated in string theory also.
In string theory, yes. But this is not a string theory answer.
I know. But then has it been shown that is it understood how to take alpha prime
No.
in that amplitude and like that?
No. That's not shown.
But ambitwister has a potential to make this connection.
Yeah, ambitwister, except that ambitwister, how to make ambitwister string theory to the regular string theory is not understood.
That is also holomorphic.
Yeah, ambitwister is a chiral, the worldsheet theory is chiral.
So is there a summation over IJK and PQR? Or?
No, PQR and IJK are arbitrary numbers. Final result doesn't depend on those, right? It's like in a string worldsheet calculation, right? You can pick 3 vertex apart arbitrarily, right? And fix them at fixed points. So it's like that, right?
So I can pick any PQ or any 3 PQ?
Yeah, any 3 PQR, any 3 IJK, fix their, so the corresponding sigma P, sigma Q, sigma R you fix at any arbitrary 3 values, okay? And you drop any arbitrary 3 equations from here.
Even that is not obvious, right? Like no matter what choice of PQ or IJK I make.
Yeah, it's not obvious, but it follows from SL2C invariance. I mean, you have to do this integral carefully and so that it has SL2C invariance, and then different choices of PQR, right? You can relate to each other by SL2C invariance.
So it's like 4 graviton amplitudes, 4 graviton string amplitudes and so on. Then this, you can show that this is in fact.
Yeah, for graviton, of course, you can explicitly calculate this,
Like
right?
you can show how this maps to the usual string amplitude and so on.
No, I don't think there is a direct map. I mean, you calculate this, you calculate from string theory, then you can compare.
Even something as simple as a 4 graviton amplitude is not.
No, I don't think there is a direct connection between string theory.
Just given this formula, is it possible to just starting with this formula, is it possible to prove that it will be independent of PQR and IJK?
Yes, yeah, yeah, it's possible.
Without assuming anything about IN?
No, you have to assume something. IN has certain transformation property under SL2C, right? That you have to assume, right? With that
And in the
input,
there is no PQR, right? It seems to depend on the
yeah, it doesn't depend on PQR. But there are two more things, S and T, there, and it will be independent of those S and T choices, right?
IN
So
has a specific SL2C weight, I think.
yeah, IN has a specific SL2C weight, and depending, I mean, using that you can show that this is invariant under this
So
choice.
is there any word line calculation for n graviton amplitude?
Word line calculation. Ambitwister, as I said, is probably the closest.
Yeah, but that is a complexification of something, of what thing? I don't remember that statement.
Yeah, I don't know if it's a complex. I mean, you can think of it as a word line calculation. See, ambitwister string itself.
It is related to supergravity in some way.
Which one?
Ambitwister.
Well, it gives the low energy supergravity, right? Just supergravity and no string connections.
Right.
Yeah.
Yeah.
So it is the full supergravity, right? So there is no word line limit of that.
No, I understand. But see, what my question is that it is related, it is connected to supergravity. It is somehow describing.
Yes.
Though there is a complexification. But from the supergravity, one could devise a word line calculation for the scattering amplitude.
I think that is okay. You can devise, but I don't think that this has been related to that at all.
No, ambitwister.
I don't think so. Yeah. Okay, so we'll be starting with this formula. Okay, so as long as this formula is clear what it means, right, we'll proceed from there. Okay, so IN I have to write. So psi ST is the matrix psi, which I am yet to define, matrix psi with ST th rows and columns removed. So S and T run between lie between 1 and n. Okay. So what is psi? Okay, psi.
But why put two STs up down?
Oh, because I mean the point is, yeah, Sth row and Sth column. I mean, that's the convention, I think. So that's why. I mean, I could have removed some other way also, right? Sth and Th rows and some other columns. Okay, because given that you have so much freedom, yeah.
Columns. One is for each for one row.
Yes. So Sth row and Sth column and Th row and Th column you remove. Okay. So psi. So this is a 2n by n 2n matrix. So AB is PA dot PB over sigma A minus sigma B for A not equal to B, and it's 0 for A equal to B. BAB epsilon PB over Okay, this is the definition of psi. Okay, so psi is a 2n by 2n matrix. Okay, A, B, and C are square matrices, n by n square matrix. Okay, this is the definition of A. Okay, this is the definition for B, and this is the definition for C.
Is SNT summed over in IN or is
No. You just drop. You took SNT and again random, right? You pick two arbitrary rows, two arbitrary columns, and you can show that IN is independent of that. Okay, this particular construction of IN ensures that if you drop that two rows and two columns, then this combination is independent of the choice of SNT.
and it has the correct SL2C weight?
And it has the correct SL2C weight to have all the properties that I mentioned there.
What is epsilon?
Epsilon, yes. So epsilon is a polarization, but it's a polarization vector.
That's what.
Okay, yeah. So then what? I mean, you have to do graviton, which is a polarization tensor, right? Okay. So what one can show is that you use this formula for psi. Pardon? No, not holomorphic. Okay. Yeah, it's more or less square root. Okay. So the point is that you take this formula, okay, substitute it here. Okay. What you find is that at the end, when you calculate the n graviton scattering, okay, each epsilon A comes twice. So the final result will always have epsilon A mu, epsilon A nu contracted with something, okay, for each of these. So that means each epsilon 1 will come twice, epsilon 2 will come twice, epsilon 3 will come twice, and so on, right? The final formula will have that structure, okay. And so take the final formula, okay, with that structure and replace this by epsilon mu nu. Yeah, it's it's not even Vierbeins because these are really vectors. A is just the number level, right?
1 to n.
Yeah, that's the 1 to n level, right? So these are really vectors, right? So the epsilons are like square roots. Okay, so the point is that you take this formula, right? It's not obvious from this complicated form that you have written that once you calculate, for example, this determinant of psi, okay, it really comes in the combination of epsilon where each epsilon appears twice. Okay.
But the number counting, is it okay? I mean, the reason epsilon A mu has only.
No, so number counting is not okay. So epsilon mu has less degrees of freedom than epsilon mu nu, right? Yeah. But the point is, once you have gotten the final formula, right, in this form, you just replace epsilon A mu, epsilon A nu by epsilon A mu nu. In 4 dimensions, it is okay, right? Because graviton has 2 helicities, photon also has 2 helicities. In higher dimension, it's certainly not okay, the number counting, right?
There is some redundant SON or SUN invariance.
Yeah, but that's so it's implicit in this formula, right? Whenever you have epsilon A mu, epsilon A nu, right? It always, of course, whatever it contracts with can be manifestly symmetrized, right?
So in their full formulation, is it manifest that gravity is square of Young-Mills?
Yes, it is manifest in the sense that gravity amplitudes can relate to Young-Mills amplitude using that formalism, right?
Somewhat like that.
Because Young-Mills amplitude, right, has a very similar formula except that instead of determinant, right, if you have some gravity and some Young-Mills, right, you have a Pfaffian here and then there is another factor which corresponds to the Young-Mills, the color in this, the color part of the amplitude.
This one is similar, somewhat like that.
Well, this one is only gravity.
Right, okay,
but you are writing the gravity amplitude in this form.
The analog of this, okay, what I'm asking is that in the formula for Young-Mills,
suppose you have pure Young-Mills,
yeah,
then you have Pfaffian times some another factor.
Here there's nothing obvious, no general coordinate invariance, nothing is manifest. It's just the scattering formula.
Yes, exactly. Gauge invariance, okay, you can say gauge invariance, you can prove. Epsilon goes to epsilon plus k, right? You can show it actually preserves this formula.
How did they get this? What was their motivation to get to this?
Well, they just wrote it down. I mean, well, of course, they had many insights from all these scattering amplitude, the analyticity studies that they have been doing, right? But when they wrote this formula, they just wrote it down.
but this one should have some interpretation, this identification of epsilon A times
In 4 dimensions, it is the standard interpretation, right?
in arbitrary dimension.
In arbitrary dimension, the point, as I said, epsilon A mu certainly has less degrees of freedom than epsilon mu nu, right?
I understand, but then when you identify, it's a prescription.
It's a prescription.
When you follow this prescription and identify it this way, it gives the right answer.
Yes.
There must be some interpretation of that.
Well, I mean, this is the formula, right? I mean, you can try to interpret it whatever you like. Right? But yeah, you can leave it as homework. But the final formula is this, that you take this formula, right? So the point is the Pfaffian, okay, you can think of this, the determinant is like Pfaffian square, right? So you can calculate the Pfaffian first, right? The Pfaffian will be linear in all the epsilons. Okay, it will be like epsilon 1 times epsilon 2 times epsilon 3 up to epsilon n, right? Yeah, size antisymmetric. Okay, so you can write it as the square of the Pfaffian. So the Pfaffian will be a linear function in epsilon 1, a multilinear function of all the epsilons. So determinant, when you square it, right, each epsilon will appear twice, right, because it's a square. So it's multi-bilinear. So you just replace epsilon mu by epsilon mu nu, right? That
actually you don't need to do anything because of what you just said. It's going to come back.
Yeah. As long as Pfaffian is multilinear, we know the determinant will be bilinear, right, in each epsilon.
The determinant of antisymmetric material is square of the Pfaffian.
Square of the Pfaffian, exactly.
So then it does seem like gravity being square of Young.
So that is to the level of the integral.
Yeah, but it's, as I said, it's square of Young-Mills, but you have the other factor. For Young-Mills is not just Pfaffian. Young-Mills also has other factor, that's a color factor.
No, there is a sense in which gravity is square of Young.
Yeah.
It is in that sense.
That's right.
But is there a sense in which the KLT relations essentially amount to this or?
Well, it's certainly related. It's clear, right? Because Young-Mills, as I said, is.
But more directly, not going through the gravity angles. So.
No, you can derive the relation between gravity and Young-Mills using this formula, right? But
KLT relations was for string amplitudes.
yeah. So no, you cannot get. These are not string amplitudes. So obviously you cannot get the KLT relation for string amplitudes, right? But the analog of KLT for Young-Mills and gravity, right, is hidden in this.
What are the checks that have been done?
What are the? Okay, I think the main checks have been in the soft limit. Okay, because one soft graviton, which I'll try to describe, okay, has been tested. So the soft limits are easy to do, right? The reason that you cannot, I mean, the direct calculation of n graviton amplitude is difficult is because you cannot solve these scattering equations really, right? These are highly non-polynomial equations. Okay, but we'll see in what sense the soft limit is easier.
But you said
You can solve one delta function.
homomorphism.
Well, we will not actually solve any delta function. We'll see. Yeah. Yeah.
Space-time gauge transformations can be checked.
Space-time gauge transfer. Meaning basically the epsilon goes to epsilon plus k mu can be checked.
K dot epsilon is 0, k square is 0.
Yeah. So
Okay.
right. So if you shift epsilon by epsilon plus k mu, right, this matrix will change. Okay, but you can show that ultimately the final result doesn't change.
And crossing symmetry is obvious.
Crossing symmetry probably is obvious because it's manifestly symmetric in all of the right.
I don't think so.
Yeah. I mean it's well. Okay.
You have to fix that overall sign
Pardon?
so carefully. Why did you have?
Oh, this one we had to fix actually because if you want the soft theorems, see soft theorem relates the n point amplitude to n plus 1 point amplitude, right? So without this minus 1 to the n, we don't get the soft theorem in the standard form.
How do you know that this is an n graviton amplitude for large n? So
Well, there are various checks, right? There is no proof that this is the n graviton amplitude.
actually there is no.
No, I think the CHI scattering formula has not been proven.
But you said but ambitwister does give it.
Well, ambitwister does give it, but there is no proof that ambitwister gives the n graviton amplitude.
But ambitwister has a relation to supergravity.
But there is no proof that that is the supergravity, right?
Apart from that, what are the checks then? Sorry, I'm still trying to get a sense of what
Mainly in the soft limit, you can calculate this, right? So I think that's one of the main checks. Yeah, that the soft limit works. And I think the other thing is that the analyticity properties, right? All the poles, etc., you can extract from here, right? The various poles correspond to degenerate Riemann surfaces, right? As you change, for example, the p's, so that some of the intermediate momenta go on shell, right? You can show that when you solve the scattering equations, that corresponds to some of the sigma is coming together, right? The degenerate Riemann surface. So the poles, you can the pole structure you can see that it has the correct factorization.
But doesn't it look a lot like a string worldsheet or something? Is that?
Yeah, I mean that was obviously their motivation, that it looks like a lot of a string worldsheet, but yeah, but it's the string worldsheet, but the worldsheet integrals are all fixed, right? There's a delta function sitting there.
get the high energy limit of string scattering.
Yeah, the Gauss-Mende formula also involved these
Becomes
exactly these scattering equations. Right, the high energy limit of string scattering amplitude. This Gauss-Mende formula involved the saddle point that they got involved solutions of this equation, same equations.
High energy.
Yeah, but again the connection between that and this direct connection is not clear, right? The formula looks the same.
And is there any version of this that has been looked at for higher spin?
No, because this is in flat space, right? And in flat space, the higher spin particles are non-interacting. I mean, you do not have interacting. Yeah, they are all trivial. So this, I mean, I think this has been used for Einstein, Maxwell, right? DBI, then what they call some adjoint scalar. Okay, so there are a whole class of theories.
What do you mean by
Dirac-Born-Infeld.
What do you mean in this context?
What is IN for DBI?
Yeah, IN for DBI. Yeah. So there is a candidate IN for DBI. Yeah.
Is IN, derived from the Lagrangian?
No. It's just given. Right? I mean,
Derive, it's not so useful.
well,
If you can derive the amplitudes, right? If you want to repackage it,
No,
understand
there is
better.
Yeah.
There are relations, various non-trivial relations.
But in the factorization, so I think the CHO originally wrote down this formula from the factorization relations. Right? This has the correct factorizations. Right? That when the momenta are adjusted so that some of the intermediate particles go on shell, right? You get the correct correct property here, factorization, from the factorization of the Riemann surface.
So there is a sense in which they sort of built up this.
Yeah, exactly. Right. So because they have been studying this analyticity structure for a long time, right? So I mean, it's basically based on that.
Yeah, if you want to say there's a lot of intuition that went in it. They don't share it with you.
No, I'm just not doing it.
Okay, so now let me say what is known. Okay, so basically you can see that if you want to evaluate it directly, right, you have to solve these scattering equations, right? And that's very hard because these are polynomial scattering equations of high degree in general. Okay, but what is known, okay, is that this has n minus 3 factorial independent solutions. Okay, so the final result can be written as a sum of n minus 3 factorial terms. Okay, if you want, if you want to evaluate it directly from these delta functions, it can be written as a sum of n minus 3 factorial terms, okay, which are the n minus 3 factorial solutions of this vanishing of this.
So this product of all the delta functions.
Yes,
That's the whole set.
whole set.
So that has n minus 3 variables.
N minus 3 factorial solution. Yeah, it has n minus 3 variables, right? And the total number of solutions of these equations is n minus 3 factorial.
A number which is not interpreted in terms of Feynman diagrams.
No. Yeah, I don't think there is any Feynman diagram understanding of this.
For n large, both the numbers will grow as n factorial, right?
Yeah.
So there is no hope that you can put them in for at least large enough n.
Large n limit, I don't know. I don't think I don't know whether people have.
No, you can't solve.
Yeah. Solving this explicitly is difficult.
Pointing polynomial, you are able to solve.
Hmm.
Maybe we can ask if anything happens to large D.
No, I was just wondering because the number of Feynman diagrams also grows factorially.
Yeah.
Number of external.
Okay, whether there's any relation between the two. Yeah, there could be. That the large growth for large n, right? Whether this can be related to the growth for Feynman diagrams. Large n growth. Yeah, that is possible. Okay. So now, how to get to soft theorem?
All the dimension dependence is only to this dot product.
Yes, all the dimension dependence is to the dot products. Okay. So what we do is that we take soft limit. So we get n gravitons of momentum yeah. What?
D equal to 3, does it make sense?
In principle, yes. I mean, you just calculate 3-level scattering, right? It's D independent, except that everything will be pure gauge, right? In D equal to 3, the graviton. There's no physical degree of freedom in the graviton. Okay, so basically we take Pi, Pn plus I equal to tau k n plus I, okay, for 1 less than or equal to I less than or equal to m, okay, and then we take the limit, take small tau limit at fixed k1 to km. Okay, so this is the way we study the amplitude. Okay, so we have to take this formula, pick the first n to be finite momentum, okay, the last m to be soft momentum. Okay, and the softness we characterize by this small parameter tau. Okay, we explicitly write the moment as tau times kn plus I, and take the tau small limit.
The first and last ordering is important for what you do?
Pardon? No, because they are gravitons, so it doesn't really matter.
First and last, or that was just something? It's just a naming. That was
This is naming, yeah. It doesn't matter the ordering. Okay, so what is the step? So let me just say the steps, okay, and then if I have time I'll give a specific example. Okay, so step 1. Is to classify solutions of scattering equations. Okay, so scattering equations are the vanishing condition of these. Okay, so these are known as the CHY scattering equations. Okay, these equal to 0. Okay, so you know the total number of solutions is n minus 3 factorial. Okay, but you want to study how these behave. Okay, in the tau goes to 0 limit. Okay, so the general class, it turns out to be the following. Okay, the general form is that the sigma is for A equal to 1 to n remain finite distance apart.
Do you really mean kn plus 1 to kn plus m or
K1 to Km.
Well, it depends on how you want to label it.
There are both of them are appearing.
Oh, okay, yeah, kn plus 1 to kn plus m. Thank you.
Call it K1 to Km.
Yeah, you could have called k1 to km also. Okay, so we take, so by analyzing the scattering equations, what we find is that the classification of the solutions is as follows. So the sigma is for A equal to 1 to n, these remain finite distance apart. Okay, for tau goes to 0 for all the solutions. Okay, then we have R1 of sigma n plus i's come within distance tau, okay. R2 of sigma n plus i's come within distance tau, and so on. Okay, so that means that the solutions cluster, so there are the sigmas, the finite sigma 1 to sigma n remain finite distance away. Okay, and then from the sigma n plus 1 to sigma n plus m, okay, what happens is that some of these come together, here some others come together, then some may be isolated. So this is the way the bunching goes. Okay, so the general solution can be classified in this way. Okay, that the sigma 1 to sigma n are always finite distance apart, and these are bunched.
This bunching is separate.
Separate.
All the soft particles are.
Not all the softs are together. Bunching happens only in the soft punctures, okay, soft sigmas. Okay, and among the soft sigmas, a certain number come together, another certain number come together, and so on.
Any partition is possible?
Yeah, I'll give you the numbers. Any partition is possible. Yeah, I'll not erase the last line. So the number of solutions of this type okay, for a given bunching, okay, for a given configuration of bunches, okay, we can count the total number of solutions, okay, and that is given by this formula, n minus 3 factorial times product over I, Ri minus 1 factorial times n minus 2.
Sorry,
Yes.
1 minute question. You are taking the general CHY prescription for an arbitrary n graviton amplitude.
N plus m graviton amplitude in this case, n plus m.
N plus m.
Yes.
And you are going to show how the soft limit of that agrees with your result.
That's right, exactly.
It's n minus 2 or n minus 2 factorial?
N minus 2 factorial.
Tau is a real number. Right?
Tau was a real number, yes.
Sigmas are holomorphic coordinates.
Sigmas are holomorphic coordinates. Tau scale the momenta.
You just want to know how you are going to take the soft.
Yeah, so tau is a real number, so the distances.
I'm trying to understand this. So what do I mean by distances between different solutions of sigmas now?
Oh, the sigmas are complex numbers, right? But
Mods.
the mods, yeah, the difference, the mod of the difference, right, is within tau, right? That's the bunching. So you take sigma n plus 1 to sigma n plus m, right? Now you pick R1 of those, imagine that they are close. R2 of those, imagine they are close. Okay, and now so given a configuration, you can count how many such solutions will there be of the scattering equation. Okay, and what we can show is that this is the number. Okay, for a given choice of the Ri's. Okay, so for example, okay, suppose you consider the solutions where all of these are separate from each other. Okay, that will correspond to R1 equal to 1, R2 equal to 1, R3 equal to 1, up to Rm equal to 1, right? Everything is separate. Okay, that number is n minus 3 factorial times n minus 2 n minus, this is not factorial. Okay, there is no factorial here. This is just n minus 2. Okay,
n minus 2 power m.
yeah, n minus 2 to the power m. Okay, that's the number of those solutions.
Total number of solutions is n minus 3 factorial.
N minus n plus m minus 3 factorial now.
Oh, right.
Is that an identity?
Yeah.
Yes. So the point is you can add up all these numbers, okay, and you can show that the total number that you get is n plus m minus 3 factorial. Okay, that's the way we can be absolutely sure that you have not missed out any solution, right? That there is no other strange kind of configurations that you have missed out. Okay, that those constitute all the solutions of the scattering equations.
So you're saying that there's some way to not be able to solve these, but somehow count accurately the number of solutions to be.
Of each kind.
What is the
Number of solutions. That I think there are various theorems. I mean, there are some general mathematical theorems. Right? That's one way to do this. The other way is that you take this and you adjust the external momenta appropriately. Right? You count the number of solutions. Okay, by say when taking one of the external momenta to be soft, and then you use the continuity to say that as you change the external momenta from soft to hard, the number of solutions cannot jump arbitrarily. Right? That's the way. That's the physicist way of counting it. But there are some mathematical theorems which allows you to count how many solutions of this there are.
This part was done before.
This part was done. So this was not done before, but the total number counting of the solution was done before. N plus m, n minus 3 factorial, right? Which in this case is n plus m minus 3 factorial.
So I'm still a bit confused about the fact that all the soft punctures bunch together, because when we look at scattering in like Minkowski, and you look at like you view the the places where the momenta as corresponding to punctures on the sphere at infinity.
Yes.
Then soft limits would correspond to one puncture going and sitting on top of a hard puncture.
No, that never happens. So yeah, so that in this from the scattering equation viewpoint, right? There is no solution where a soft puncture goes and sits on top of the hard puncture. That you can check, right? That the soft punctures come close to each other, but never on top of the hard puncture.
But these punctures should not be identified with the punctures at null.
But even there it
No.
No, there it happens, right? If you look at the soft momenta, then the softness will correspond to this puncture going and sitting on like a hard.
Nothing to do with
What is that momentum about collinear?
Yeah, there will be some special limit.
Meaning the hard puncture, see, I mean, if you take external stress to be massive, then the hard particles go into time like infinity, right?
Right.
So then the soft particles are not going to sit.
Oh, that's true, but
And-
I was talking about masses.
So even there, I mean, the directions are arbitrary. Why should they have anything to do with the
See, first
direction?
of all, this punctures and the momenta, they don't really have anything to do with each other.
Yeah.
Except that these sigmas are solutions of this
Of this equation, yeah. So this is just a mathematical statement that,
So yeah, for every zero, I can write as a functions of like all these PIs, and so when a bunch of them are becoming zero, obviously those solutions like those will probably kind of bunch together.
yeah. So that's all all happens, right? And as I said, you can count the total number, and you can show that this total number adds up to n plus m minus 3 factorial.
You take this, this argument of the delta function.
Yes.
Some of them are hard, and some of them are soft.
Yes.
These softs are always together.
No.
P's, two P's, both the two P's
Yeah.
are scaled by
Yes.
tau.
That's
So
right.
It's of order tau square.
Yes.
And then you somehow do that.
Analyze the
tau,
solution.
the small tau limit.
Yeah.
Somehow is the
So will the identification be that 1 by tau square is the leading and 1 by tau will be...
Well, actually, for m soft gravitons, 1 over tau to the m will be
Tau to the
leading.
m, sorry.
Yeah.
From each, I was just...
Exactly. Yeah. Okay. So the step 2. So this is the step 1 to identify the solutions.
So this is one type of configuration. So there are other type of configurations as well. Like
No.
hard configurations,
Which configuration?
hard configurations, soft hard configurations.
No, these are all the solutions. The total number of solutions that you get by adding of all these in n plus m minus 3 factorial.
Of this type of solutions.
Of all types of solutions. Total number of solutions is n plus m minus 3 factorial, right?
Oh, because if you count them, then it saturates the total.
Exactly. So you know that there are no other kinds of solutions. Okay. The only kind of solutions, okay, are whether all punctures are separate. That corresponds to R1 equal to 1, R2 equal to 1, up to Rm equal to 1, right? Or some soft punctures are bunched together. Okay, and when you add up all their numbers, you get n plus m minus 3 factorial. So there is nothing else.
So with this scaling, you started counting the number of solutions and then saw that soft will exhaust all of them.
Exactly.
So all you have to do now is to identify which of these gives the appropriate power of tau.
That's right. Yeah.
Class of these.
Yeah. Which subclass of this? Okay. So the step 2 is approximate the integrand as tau goes to 0. Okay, and here of course we need different approximations for different classes of solutions. Okay, and the reason is that if you recall, both in the argument of the delta function, okay, as well as in the expression for the determinant, right, at in, okay, there is a 1 over sigma a minus sigma b factors. right? So if sum of the sigma minus sigma v is becoming small, okay, then even if there is a tau in the numerator, they can cancel it, right? So for a given class of solutions, you have to carry out the appropriate approximation scheme. Okay, that you cannot do a overall approximation of the whole integrand once and for all. Okay, so different solutions you make different approximations. Okay, and here one finds, okay, so the result is that up to subleading order, only two classes contribute. Okay, so one is R1 equal to 1, R2 equal to 1, up to Rm equal to 1, which means all are separate. Okay, nothing bunches together. Okay, so this is called the non-degenerate solution. Okay. And the second one is R1 equal to 2, and then everything else is 1.
In partitions, it's simpler. Right, it is 1 power n.
Yeah, okay. Yeah. 1 power m and yeah, 1 power m minus 1, 2 and 2. Is this clear? So the non-degenerate solution is where all the sigma is are finite distance away from each other. The degenerate solution is when two of the sigma is are close, all the others are finite distance away from each other. Okay. This one starts contributing at the leading order. Okay. This one begins contributing at subleading order.
Here leading, subletting, these are powers of tau.
Powers of tau. So leading is 1 over tau to the m. Okay. Subleading is 1 over tau to the m minus 1.
Suppose there's the three of them coming together might be the next order.
Yeah. So in the next order, the three of them coming together will start contributing.
No, but there you have more possibilities. You can have 2, 2.
Yeah, 2, 2 is, I think, if I remember correctly, 2, 2 will be even higher order.
Even higher.
Yeah, I think 2, 2 will be in higher order, yeah. Okay, but I'm not completely sure because we didn't really carefully analyze the next order. Oh, I think I can erase it. We have seen it for sufficiently long time. Okay, the point is that even after doing all this, okay, we still cannot solve the scattering equations. Okay, so we have to do some work to figure out what to do.
But you need to just get it to in minus 1, in minus n or something.
Yeah, we need to get it to in minus 1, but still we cannot get it by directly solving the scattering equation. Okay, because that's still complicated. Yes. No, ordinary quantum. This is a formula for ordinary gravity, right? Just pure Einstein gravity. Yeah, tree-level perturbative gravity. Yeah, exactly. Tree level. Yeah. This is only tree level. Yeah.
Your theorem was very different to loop.
Yeah. So this is just checking the tree level satisfies that. Yeah. Okay. So now the next step. Okay. So after making the approximation, okay, we represent delta function integration as contour integrals. Okay, this is what I described in the first at the beginning, right? How to represent delta functions as contour integrals. Okay. And then evaluate integration over sigma n plus 1 to sigma n plus m by deforming the contours to infinity.
You can't really associate certain zeros with certain momentum legs, right?
No, no.
Okay, so
It's-
n plus only n plus m, how do you decide which of them?
Well, the ordering, we make we had a product of delta functions, right? And the product of sigma is, okay? So that using that ordering, we associate this, right?
Some arbitrary fashion.
Well, some arbitrary fashion, meaning the
It is not arbitrary because
because you have a P1 to Pn, right? We use the same index A for P's as well as sigmas, right?
Right.
Even though it's not that,
So that's all you mean.
yeah,
Okay.
exactly, that's the connection.
But other than that, like now that say like just because you labeled 1 0 with some 2 doesn't mean that has anything to do with the second leg or anything.
but it does in the form.
Meaning, okay, since you don't know how the formula comes, right, from any fundamental principle, you can say, okay, it's arbitrary, but at least in the formula there is a ordering of the sigmas as well as ordering of the p's, right? So from that point of view, no, there is a connection.
And that overall sign can be fixed for a particular small number of gravitons.
Yeah, overall sign of course can be fixed for a small number of gravitons. Okay, so this is the point that we cannot evaluate the contour integrals directly, okay, because we cannot solve the scattering equations. Okay, but contour integrals can be deformed. Okay, so instead of trying to find where the original poles were, okay, we try to take the contours to infinity, and in that process pick up whatever other poles it encounters. Okay, residues are the other poles, and possibly residue at infinity. Okay, so that's the way we evaluate this. So that doesn't require solving the scattering equations.
Because others are not fixed.
Pardon?
I don't understand.
See, if you have a
contour integral on some fixed point.
yeah, suppose you have a integral d sigma over f of sigma, right? D sigma integral d sigma over f of sigma times f of sigma. Okay, over some sigma alpha, which are the zeros of f of sigma, and you don't know what these are. These are complicated objects. Okay, so you start deforming this contour away from the sigma alphas. Okay, and in that process you will pick up the poles of the f of sigma, right? Which may be easier to determine.
Yeah. So.
And in this case, they are easier to determine, right? That's the way you evaluate these contour integrals.
Yeah. In this case, those will pick up contributions from the other punctures, right?
From the INs, basically.
From the INs, I see.
Okay, the INs are poles.
Oh, okay. I see.
Okay, in general, it's a complicated expression. You have to look at the pole integrand. Okay, but those are the poles that you will encounter on the way. Okay, and then you evaluate this by residue theorem.
This trick is useful only for soft graviton?
Yeah, this is useful only for the soft limit, because otherwise this doesn't simplify. You don't get any simple formula by this procedure.
But this is like you have some contours. So this f sigma is like sigma minus some sigma alpha type of.
Yes.
Right? Small f sigma is sigma minus sigma
Yeah.
alpha from type terms. So whatever the values of sigma minus sigma alpha without scaling or anything, you could do this contour argument anyway.
That's right.
Yeah.
Yeah.
So why is soft?
Because there are multiple contours, no? The first contour you may be able to do. Okay. Second contour when you try to deform, okay, they are very complicated functions with complicated poles.
Yeah. So
Okay.
for soft graviton, what happens?
So for soft graviton there is a factorization. Okay, there you have a product of functions, right? And each function. So the point is that before you start doing this contour integral, right, you already do the approximation.
Yes. The
Integrand.
Yeah,
Okay. That in that approximation you have already expanded in powers of tau and kept up to certain powers of tau.
Yeah.
Okay.
Still, there are we know that this, for example, number one.
Yes.
All these soft punctures are separated.
That's right.
Are separated or what?
Yes, they are all separated.
They are all separated.
Exactly.
And we don't know the locations.
We don't know the locations.
So where is the factorization?
There is a factorization. Yeah, you approximate the integrand. Okay.
Oh, I
Because that the delta function will go like
Yeah.
tau.
Meaning, if I have some time, I can show you. I mean, for the leading soft theorem, how it works, right?
That expression, but if you do this approximation in powers of tau, if you expand it,
Yeah.
you will get some simplification.
Exactly.
In that, there you can use.
And there, if you deform this contour, right, on the way, you can show that you pick up the appropriate residues, okay, and that's what gives you the final answer. Okay, so basically, this is what the final result. Okay, this precisely gives the.
The fact that
Yeah.
you express things in terms of I n minus m, is it related to this?
In basically. You start from in plus m, right? Yeah. So basically you try to do the sigma n plus 1 to sigma n plus m integrals explicitly, and then you show that whatever is left behind, right, in terms of sigma 1 to sigma n, okay, with these three things dropped, that's exactly in. Okay, it's some factor times in. Right? That's the way you prove
That's why
this.
for you the signs were important. I
The
think the signs were
yeah, exactly, because you are relating in plus m to in, right? So the signs were important.
Soft graviton theorem is basically equal to certain mathematical properties of the light,
Yeah.
full structure or something.
Yeah, full integrals. I mean, in the approximation, when you take the tau, when you approximate the integrand in the tau goes to 0 limit, right? Certain simplifications occur. Then you can deform the contour. Okay, you can pick up the appropriate poles. Okay, and the residues precisely produces the subleading soft graviton theorem.
So from this point of view, why does the next order not work?
No, from this point of view, probably you can carry out an next order analysis, right?
For a particular theory.
Yeah, it's not universal. I mean, you know from general analysis that the next order is not universal, right? But this procedure probably can be done for the next order in Einstein theory. Right? But that relation will be very specific to Einstein theory only.
But Ashok, we don't know if this determinant corresponds to Einstein-Hilbert gravity, right? It could have R square in principle also.
No, this determinant, this particular formula,
Yeah.
you are saying how do you know that this is, I think the scaling, I mean you can probably check the scaling of the amplitude when you scale all the external momenta, right? And if, I mean it scales without any extra, I mean it scales as if the theory only had two derivative terms.
Okay, then it's just
Yeah, because if you had hard derivative terms, right, then the scaling property will be changed, right?
Sorry, what was the question?
That how do you know that this amplitude that you are getting,
the integrand.
the CHY formula, that is only for Einstein gravity and not for say Einstein gravity plus hard derivative corrections.
For CHY to answer.
Yes, for CHY to answer exactly.
So what was the answer?
So the answer is that I don't know for sure, but I think the point is if you take this CHY formula and ask what happens when you scale up all the momenta, right? I think it has the appropriate scaling property which shows that there are no higher derivative terms in the action. Right? If you have higher derivative corrections, then the scaling will be different, right?
Every higher derivative term will require a new scale, right? Like
Yeah, exactly.
or something.
That's right.
So for the
And this one doesn't have any new scale.
for dBi,
Yeah, for the dBi, I think somehow you can write it in a way, right? In a scale-free notation, yeah. Which, yeah, I don't remember now exactly. I think that there is an intrinsic scale in the definition of in, which goes in, right? Because the dBi in is different from what I wrote here.
all powers of G Newton also are the same because they sit outside.
In this case, yeah, G Newton for a pure gravity scattering, right? G Newton is just an overall factor that will appear in this matrix, right? Yeah, it's just tree level. Yeah.
Something related to this, like instead of Einstein action, I can have something allows to Born-Infeld for the gravity, right?
Well, I think Born-Infeld for gravity, yeah, some people have tried, but I don't think there is any really good understanding of what it will correspond to.
So writing the tree level diagram, I can still kind of write the theory and just as I do it for Born-Infeld, I can do it for the gravity and just write the tree level diagram and
Yeah, you can write it. I mean, or any other higher derivative terms, right?
No,
But
it's
this,
not exactly higher derivative in the sense of just like Born-Infeld is not really like higher derivative case theory.
well, see, it is still higher derivative in the sense that writing the Born-Infeld action introduces a new scale in the theory,
Fair enough.
right?
But it is quite different from writing like some whole lots of derivatives acting on the gauge field. under.
Yeah, it's not derivatives acting on a gauge field, but it's higher parts of the gauge field strength, right? Higher parts of F mu nu.
Yes.
Okay, so if you calculate the scattering in bond-in field, right, it will not have the scaling property that a pure gauge theory scattering will have, right?
So yeah, I mean, if you're saying that like, you can distinguish one from the other, yes.
Yeah,
If you know
yeah.
the structure of
So if you look at the CHY scattering, right, I think by looking at the scaling property of the CHY formula, you can figure out that it's Einstein-Hilbert and not Einstein-Hilbert plus R derivative, right? Or that it's Einstein-Maxwell.
When you say CHY formula, do you mean IN?
IN, a given IN.
I mean, if you know what IN is, like presumably you can deduce from it.
Exactly, that's right.
Is there any understanding of changing the Riemann surface and hoping that you get some higher loops or anything like that?
I think there's a lot of work going on, right? But I don't know whether there's a very concrete understanding of the loop corrections in CHY.
But presumably these are all nice functions in PA.PVs.
Yeah. Yeah, meaning after all, they are given in terms of Feynman diagrams.
And they satisfy what identities or what not.
Yeah, except that see for loops, I mean you will encounter ultraviolet divergence, right? So if you want to define the loop correction in pure gravity, right? What you can probably hope for at most is that you may get the integrand from a formula like this, but then you have to do the momentum integral, and there you have to worry about how to take into account ultraviolet divergence. Yeah, exactly. Yeah, because loop for pure gravity will encounter ultraviolet divergence.
So any work on trying to understand if this integrand satisfies any recursion-like insertion?
Recursion.
Some, like nn plus 1. In the soft, I guess it's here.
In the soft limit, yes. But
Here's for all n as a closed formula.
yeah, a closed form. Yeah, and upon it has the correct factorization properties. Right, I mean that was the one which went in.
So if it has right factorization properties and its gauge invariant, then it has to be right. Is that unique?
I don't know. I think at least it's not clear that fixes it completely.
For example.
Yeah, it's not fixing IN, so you have to also look at for 3-point functions.
Given IN.
Yeah, given IN and gauge invariance.
Can you say that that's for Einstein graph?
That's why the property is required.
There is no
I think
scale.
given
limit.
IN,
Yes,
probably there may be
there is no
some
extra
reducing
scale.
variance.
Yes.
Then it is. That is the unique two derivative. Einstein gravity is unique.
Yeah, maybe there is an indirect way to prove that you have given a formula, right? I don't know. At least the claim is that it's still a conjecture. Okay, I don't think that people have claimed that it is a proof of this. CHY, yeah, it came as a conjecture. Yes.
What is the conjecture?
The CHY scattering formula.
Yeah, but you said whether there is a proof or not. What was the
I don't think there is. There is a claim that it has been proven.
that this is the Einstein gravity
Yeah,
result.
that's right. That people have carried out lots of tests, right? But a generic proof that this is the Einstein gravity result, I don't think that that exists yet.
Do you think it's practical to show us an example, or will it take too much time?
Well, I can do it. Meaning, you can tell me when to stop. I have 2 pages.
Okay, if we want to ask one more question, I make it.
Okay, should I do that?
The 2 pages means what are you going to talk about?
No question.
The example that how to get the I'll do the leading soft theorem, leading single soft theorem. Maybe that's
Yeah.
right. That will give the idea of how it goes.
So before that, you please tell again what you said about the loop. You said something about the loop.
Well, nothing is known about the loops. Something is known about the loops, but no
Very strict
concrete.
time.
No, we are past the time. That's why
That is right.
it's 5. So
It's over anyway. So why?
no, but let us finish this.
Yeah. Yeah, but the point is, I'm not going to talk about loops. So, this will be all 3. Okay, so leading soft theorem, leading single soft. Okay, this of course has been known for quite some time. Okay, but I'll just say how one does this, right? So we define d sigma as integral product c equal to 1 to n c naught equal to pqr Okay, and the point is we choose PQR and IJK from 1 to n. Okay, from the hard ones.
So you don't have to touch it.
Yeah, so the soft one you don't soft one doesn't enter here. So then mn plus 1. Okay. So it's now a function of p1 to pn and tau kn plus 1, right? So one can show that this becomes of the following form. We have d sigma integral d sigma n plus 1 Let me write sigma A minus sigma B. Okay, this is a rewriting of what we already had. Sorry, yeah, yes, there is a double delta. This okay, so this is the formula, okay, and in plus 1. Okay. So the idea is that here we know that in the tau goes to 0 limit, okay, all the sigmas are separate. Okay, from this general formula that we had seen, we know that the only solution is when all the sigmas are separate. Okay, so this means that sigma A minus sigma n plus 1 remains finite. Okay, in the tau goes to 0 limit. So you just cross this out. Okay, in the leading contribution, in the sub-leading order, you have to expand an Taylor series. Okay, but in the leading order, you can just cross it out. Okay, and this tau. Okay, we can take out, sorry, this tau we can remove and we can put a 1 over tau, right? Because delta x is 1 over a times delta x. So this tau we can just take out. So then one can show that in small tau limit, okay, we use the formula for in plus 1. Okay. This becomes sum over minus okay, this is, you just look at the expression for in which has the determinant, right, and evaluate the determinant in the appropriate limit. Okay, again using the fact that this object, okay, the difference between the sigmas always remain finite, right, because that's the only solution that is relevant here. Okay, for one soft graviton, that everything remains always finite distance having. So now basically we put this in this formula, okay, and evaluate it. So let me write down the formula for mn plus 1. So you get minus 1 over tau integral d sigma Okay, it's I think more or less clear what we have done, right? We drop this, right? We just rearrange things, so this part doesn't depend on sigma n plus 1, so you could take it out of the integral. Okay, I just pull this tau out. Okay, and then for delta function, I just wrote the inverse of this function and represent this as a contour integral. So this contour is around zeros of this function, zeros of this object. Okay, it's f of sigma inverse. So the idea is that in the sigma n plus 1 plane, we have this complicated, these are the solutions of the scattering equation. Okay. This contour, okay, basically wraps the solutions to the scattering equations. Okay. And then there are other poles. Okay. These poles are coming from this object over here, the in, or from in plus 1, right? You factored out in, whatever this multiplicative factor was, this factor. Okay. This factor has poles, and those are the poles in which are the extra poles of the integrand.
Why can't they be inside that contour?
Well, the contour is chosen so as to avoid them, right? If they are here,
Oh yes.
you will take the contour like this, right? Because this contour by definition only wraps the poles of this.
So there can't be any common solutions to those two equations?
No, in general, for generic momentum, right, there can't be any common solution to those two equations, right? Because those two equations correspond to sigma n plus 1 going to sigma b, right? And you can check that that's not a generically that's not a solution to the equation that sigma n plus 1 is supposed to satisfy. Okay. So now the idea is that you take this contour and expand it out. Okay. In that process, you will pick up these poles, right? But these poles are easy to identify, right? These poles are at sigma n plus 1 equal to sigma a. Okay. See, the zeros of this are very hard to find, right? But poles of these are easy to identify, right? Sigma n plus 1 equal to sigma a. Right? You just pick up the contribution.
Those precisely correspond to the when you can identify these with momenta going to the momenta. The sigmas going to the
Yeah, these correspond to sigmas. Yeah, exactly. When you deform it. Okay, so deformed version corresponds to soft sigma going to hard sigma, but not the solution to the scattering equation is not that sigma n plus 1 goes on top of sigma.
Plus possibility of infinity.
Yeah, exactly. Okay. So these contributions will correspond to the soft line attached to a hard line. Okay, in the Feynman diagram language. Okay, but you can see that the Feynman diagrams are not directly related to the solution to the scattering equation, right? Because a residue here will be a complicated combination of the solution to the scattering of these contributions. Okay, so now it's easy, right? We just look at the residue at sigma equal to sigma a. So it will look like there is a double pole at sigma n plus 1 equal to sigma a, right? This looks like it has a double pole, right? But there is actually 0 from here, right? Because this thing has a pole at sigma n plus 1 equal to sigma a. You are taking the inverse of that. Okay, so it's really a single pole. Okay, so the residue is easy to evaluate. So the formula for m n plus 1 is 1 over tau integral d sigma pardon?
You just call this big thing some x.
Yeah, I'm going to, well, this is the only part time I'm going to write it, so it's okay, one more time I can write. Okay, so this minus sign you can see has gone, okay, because the contours are now reversed, right? These were anti-clockwise contours, right? When they wrap the other ones, it becomes clockwise contours, so that takes care of the minus sign. Okay, so this minus sign to begin with came because of the minus 1 to the n in the expression for in plus 1. Okay, so that when you relate in plus 1 to in, okay, that is a minus 1 to the n plus 1, that becomes minus 1 times minus 1 to the n, right? That's the way we.
So when you mentioned this, there's no pole at infinity, sigma.
Well, yeah, so that's something you have to check. Okay, in this case you can show that there is no pole at infinity. Okay, but for multiple soft, okay, individual terms do have poles at infinity and you have to keep track of them. Okay, it turns out eventually they cancel. Okay, but individual terms do have poles at infinity.
Multiple problems, you will take sigma n plus 1, sigma n plus 2 and do your usual
Exactly.
delta function rules and so on.
Yeah. So you basically deform one by one, right? First take sigma, deform sigma n plus 2, then you deform sigma n plus 1. And now it's more or less done, right? Because this factor, you can see that now this integral can be done independently of this, right? This doesn't depend on any of the sigmas. Okay, the sigma dependencies cancel out. So this one, if once you use the fact that epsilon n plus 1 mu, epsilon n plus 1 nu has to be thought of as epsilon n plus 1 mu nu, right? The graviton polarization. Okay. Then this just becomes sum over a equal to 1 to n epsilon a, sorry, epsilon n plus 1 mu nu pa nu over k n plus 1 dot pa. Right? This is exactly the S0, what is called S0, the leading soft factors. And this whole integral is Mn.
The minus signs were important for you to get this with the right sign.
Yes, that's right. Okay, so I think that's it.